This is my first time lecturing to an empty room. It's a very weird feeling. Hope it works out filming wise. Today's a holiday and I figured the camera system would still activate, and I don't know. And I thought it would be fun to do a bonus lecture. Because there was a bunch of stuff that I really wanted to say in the course, and I just don't have that much time. I don't really get nervous when there are people in the room, but somehow this is very nerve-wracking. With an empty room. Anyways, I want to talk about some extra linear regression stuff. So I prepared this bonus lecture. Hopefully you can see it. There's a lot of things I want to talk about, and I hope the camera's rolling for about 55 minutes, so I'll just go really fast, and I guess there won't be any questions, so that'll save time. Okay, first thing I wanted to talk about is this issue of L2 and L1 loss has a connection to mean and median, which you may know, but if not, I think it's good to know. And so here's what I'm going to do. Oh, so the mean is a value that minimizes the L2 distance between itself and a bunch of numbers. And the median is that same thing for L1. So look at this. What's up with the cursor? Why is there? Whatever. Okay, so I create a bunch of numbers. I just pick them pretty much arbitrarily. And then I can compute their mean and median. And then what I'll do is I'll define functions for the L1 loss and L2 loss, and I'll use the minimizer built into Python, or built into SciPy, to minimize those losses with respect to the difference from the numbers, and 0 will just be my starting guess. And I print those out, and you see I pretty much get the same things, 23.2 and 4. So that's just a quick note, if you hadn't heard of it before, that another way of defining the mean of a bunch of numbers is the quantity that minimizes the sum of squared distances between it and all the other numbers. And likewise for median and absolute value distance. And why do we even care about that? Because the intuition sort of carries over to robust regression with the absolute value loss, which we talked about in the course. So you may have heard that the median is robust and the mean is not robust, and that kind of makes sense because if I change this 100 to 1,000, the mean will go way up, but the median will stay the same because it's still the middle even if I move that number away. And that intuition actually carries over to our robust regression with the L1 loss. I guess one reason why I'm nervous is I'm not actually sure it's filming and not that sure I know how to set up the camera because I don't usually do it. But anyways. Okay, so you can carry over that intuition to robust regression. So here's some code that generates some synthetic data in 1D. We saw this before, so I fit it with the Huber. It's robust. I fit it with least squares. It's kind of crazy. And now I can ask the question, what happens if we make one of the outliers really huge? So look at this line of code is setting y0 to 1,000,000. So that's saying, that's analogous to what I said with the mean and median. Take one number and make it huge, right? So check it out. Great. Notice the change of scale on the y-axis, okay? You may think the orange least squares line didn't change, but it did change. It what crazy change, because look at the change in the scalar. I guess in the videos, picture of me is to the right of the image. So if I want to point to the image, I guess I should point over there? No, over there. Yeah, I think so. Okay, look over there, and you will see that the L2 loss regression line actually changed a lot. I made that one outlier 1,000,000, and that line got pulled because look, it goes up to pretty much 200,000 here, and before it only went up to 50. So, and yet the Huber line stayed pretty much the same. So that's cool, and it's exactly that intuition that it's doing a median-esque thing, and in fact, you can prove that the line's really not changing. Okay. So here's another question. For that same crazy data set, you can look at the residuals, meaning the difference between the predictions and the training target values, take the absolute value. The first residual is huge because we made that point equal to 1 million, and the rest are really tiny. And so, as I said, this mean and median intuition sort of explains why those residuals stay really tiny. But this way of thinking of it is, let's say I allowed the line to be pulled up by that outlier. And let's just, in our heads, think about the L1 absolute value loss because it's less complicated than the Huber. Then the loss from that one point, let's say I move it up by epsilon. Then the loss from that one point is decreased by epsilon. So that one point is happier by epsilon. But all the other points are unhappier by epsilon because I pulled the line away from them. So my overall loss will go down by epsilon and up by n minus 1 times epsilon. So it's going to be worse than it was before, and that's why I'm not even going to shift the line by any amount epsilon. So that's the intuition for L1. Whereas with L2, if I shift the line by epsilon, now my loss from that outlier goes from 1 million squared to 1 million minus epsilon squared. That's a huge difference because the parabola curves upwards. And that, whereas the other ones, the quadratic on the other hand over here is very flat. So if I go from 10 to the minus 4 to 10 to the minus 4 plus epsilon as my residual for those other points, they don't really care because when I square those, the difference isn't big. So that's an intuitive explanation of this robustness. How are we doing for time? We've hit 2 of the topics in only 5 minutes, so I guess we're ahead of schedule. I would have asked for questions. It just seems like I should, but I guess I'll just keep going. Okay, by the way, this second thing I just talked about is in this, one of my demo notebooks. I just never had time to go through it or talk you through it as I'm doing now. Okay, next. This is also something that's in the slides, but I just wanted to say it, which is this whole issue of basis functions. So we were drawing these polynomial basis functions and these RBF bump basis functions, and I just wanted to say mathematically where are those pictures coming from. So the linear regression is y, predictions are y equals y hat, because it's a prediction, equals, I'm not going to have time to add all the hats, just propagate the hats, equals x times w or z times v in this special notation we use for transformed features. So we usually think of matrix multiplication as this row-wise thing. So y1 is the first row of z times v, y2 is the second row of z times v, and so on, which really makes sense because the output from the first training example is the input from the first training example times v, output for the second example is input from the second example times v. That makes sense. But this column-wise view of matrix multiplication, I find, is also useful in understanding this basis function thing. So the column-wise view of matrix multiplication is that this vector y is the first column of z times v1 plus the second column of z times v2, and that's what's written. And those superscripts z1, z2 are just the notation for columns. Somehow I slipped into my American talking, even though I am Canadian. Okay, so right, but where does that first column come from, like Z1 or Z2? Well, remember when we transformed our features, we made up these new features. So the first column of Z was our made-up feature number 1, and the second column of Z was our made-up feature number 2. For example, linear term, quadratic term, cubic term, etc. So we could write this as, instead of the first column of Z, as our first function of x, right? Because that's where we made these features. So our first function of x is the first column of z. Our second function of x is our second column of z, and so on. That's really what we were doing with polynomials and everything, right? So we can write it this other way. Y should be a hat equals v1 h1 of x plus v2 h2 of x. And now we can see why we're saying basis functions and why we're saying it's a weighted combination of these basis functions. Because imagine x is, say, a grid of points, or your x test. Then you're calling that function on h1 of x becomes like that function applied to each x. So if h1 is quadratic, then h1 of x is going to look like this, and if h2 is cubic, h2 of x is going to look like this, and so on. And those v1, v2, etc. are scalars. So it really is kind of a weighted combination of these basis functions. But the reason why it's so confusing, I think the key confusion issue here is that when we think of training, we talk about training, we're just evaluating these functions at our training points. So I think it's helpful to think of what the test matrix looks like, and especially what the test matrix looks like when our test points is a grid, and then you make a plot of it, and you see you're really learning these functions. Even though there's none in the room for me to get vibes from, I kind of feel like this section was less clear than the first two sections, and indeed there are no pictures, and it's usually good to have pictures. So, oh well. Okay, maybe it helped. Next part, Gaussian RBFs. Yet another thing that I wanted to go into detail in, but didn't have time because I had to rush through in class. So I produced this Z matrix for you. It's the same one as from the slides in class, I hope, unless I mess something up. But I just wrote it a little differently, which is I wrote the tildes on top of the x's to emphasize the test point. So I wrote the test matrix, and I guess I could put tilde z to just be very clear about that. And so first let's talk about the layout of this matrix. Let's look very carefully. Each column of the matrix has the same training example. The first column has x1 appearing every time. The second column has x2 appearing every time. This is kind of the transpose of what we're used to, where we think of row 1 as first example, row 2 as second example. That's still true, but not the pattern we're observing. So the reason is, in our feature transformation, we have created one feature per training example. So if we have n training examples, we have n features. And that's why the non-tilde part, just the x, which means training example, right? Tilde means test example. The training examples are going x1 is the first column, x2 is the second column, x3 is the third column, all the way up to n, and indeed we have n columns. And so that kind of makes sense. And as always, if we have t test examples, we should have t rows to our data matrix, one per point, as usual. So that's why the tilde ones are incrementing kind of downwards, and the non-tilde ones are incrementing, I guess, kind of horizontally, left to right. So that's what the layout of the matrix means. But what's especially confusing, and I think what was on the slide that I originally showed you, is that it was showing you the training Z. And for the training Z, the tildes, the points at which you are creating this transformed feature matrix Z are the training points. So in other words, x tilde is just x for training. And then you get a symmetric matrix because you have n rows, n columns, and when you look at that, you might forget which way it's supposed to be. But when you write it this way, it's very clear and emphasized that the training goes across. So you have n training examples, so you have n columns, and the test points go down. So the Z matrix will be symmetric in training, but isn't in general. It's not even square in general. Because it's just features, right? So you can have a feature vector even for one test example. Okay, so that's what does the layout mean? What is the layout of this matrix? But also I want to talk about what do the entries mean? So what is this G parentheses bar X? It's quite a mess, right? So let's talk about it. The double bars are norms. We already know that. So that is, you could think of the distance between the two things. So as I go down, say a first column, it's the distance between all my points and the first training example. That's the first feature. So it has something to do with, for all my points, the distance between those points and the first training example. And what we want is we show those pictures of those basis functions where there's little bumps. So what we want is something that is bigger when the distance is 0, because we want a bump centered at the training example. That's what the RBF features are. And how should I say this? Okay, we want a bump centered at the training example, so we want a function that is big when that distance is 0 and falls off as that distance gets big. So this G function, in this case we're doing the Gaussian RBF, that G is basically the Gaussian function, e to the minus x squared, basically. That function has the property we want, right? It's big at 0 and goes to 0. So then it makes sense to take G of the distance between the points. Then that's the same as saying we have a bump centered at the point, because it's big when x equals the point. And by the way, x doesn't have to be one-dimensional. So x1 tilde and x1 could be vectors. So you actually can have basically a d-dimensional spherical bump that falls off in d dimensions away from the data point. But we mostly talked about it in the one-dimensional case. Okay. So this epsilon in the picture here, that's just a placeholder. I could have said g of x equals, but we just used x too many times. So that's all that is. Sigma is a hyperparameter that says how quickly does this thing fall off. So I think sigma goes to 0 is an interesting case. When sigma goes to 0, you have this infinitely thin bump. It's like a delta function, if you're familiar with delta functions, at the point. So when sigma equals 0, we can, assuming, say, the bump has height 1 and then instantly falls off to 0 everywhere else, we have n features, so we could just set v equal to y. Because, why is that? Well, we have v1, our first coefficient, times the first basis function. So it's just going to be an infinitely thin bump scaled up to exactly land on our point, and it'll be 0 everywhere else. And then for the second bump is something centered at the second point. So we scale it up by v2, which equals y2, and it'll exactly pass through that point. Again, a picture would have been helpful. We did actually see a picture like this in the other notes, so you can go back to those notes, or in the notebook, which is, I guess, lecture 14 demo, probably, or maybe 15 demo. But so when sigma equals 0, you basically you can make each bump just the height of the actual y value, and it'll be infinitely narrow, and then the regression surface you'll learn will be really weird. It'll just be the true values at all the training points and 0 everywhere else, which is a ridiculous thing to learn. I wouldn't even really call it learning. But it's useful to think about that to understand why this bump centered at thing actually makes sense. It's just saying, I want to be able to hit those targets with the training point. So by centering a bump at the x of the training points, I can hit that target. I can pass through the training point by making the height just right. And then away from the training points, well, I don't know. I don't have data there. I don't know what's going on over there. So let me not say as much about it, which is why the thing falls off to 0. But then when you make big sigma, then the bumps fall off more slowly, and if you have enough data that the bumps are close enough together, because the data is close enough together that they kind of touch each other before going to 0, then you get these smooth curves that we saw instead of just these tiny little bumps. Okay, would like to ask if there are questions again. In this case, unlike in the previous case here, I feel like I did an okay job of explaining it, and yet wouldn't be surprised if it's still confusing because it's just a complicated thing. And had I had my act together and taken the nice pictures from the other notebook and had them here, that would have been useful aid. That is life. Okay. Cool. Cool beans. Making progress. Okay. Regularization, strength, intuition. So I want to think about what does it mean to change lambda. Let's take a very simple case where n equals 1, d equals 1 means 1 point, 1 feature. And furthermore, the point is at 1, 1, and furthermore, we have no intercept. So that's our data set, okay? Just the 1 point in 1 dimension at 1, 1, and that's our best fit line. Whoosh, just passes through the point, okay? So let's draw the loss. The loss is, in this case, something ridiculously simple. X is 1, so 1 times w minus y is 1. So 1 times w minus 1 squared is our loss, plus lambda w squared with L2 regularization. So what I want to talk about is how the left-hand term, the data term, wants to set w to 1. In other words, if you didn't have the regularization, that's just a quadratic. Its minimum is when w equals 1. The right-hand term just wants w to be as small as possible because it's a parabola centered at w equals 0. So those two terms are kind of fighting each other, and I think it's very helpful to actually think about it that way. And furthermore, think about lambda as controlling who gets to fight harder. So, in fact, because this example is so simple, I can do the math just by hand. I can really just take the derivative of that thing. It's not a gradient. It's just a derivative because I only have one parameter, w. I can set it to 0. I can solve. The math isn't really the point right now, but the point is what I actually get, which is 1 over 1 plus lambda, which looks like this. That's the function, 1 over 1 plus lambda. So we saw regularization paths in the lecture. We had all these weights, and they were changing with lambda, and they were converging to 0. So this is that. It's a regularization path with just one weight, because we only have one weight. And it has those limiting cases that we expected. When lambda is 0, w is 1. Excuse me. That makes sense because we just said before, w wants to be 1. It wants to be that straight line. Line of slope 1, if there's no regularization, it's just going to do that. And if there's infinite regularization, the other term wins. The w minus 1 squared becomes essentially negligible compared to that other such big term, which just says lambda w squared, and so we just push w to 0. Okay. So another question is what happens as n gets large when you're regularizing? And I think the intuition I'd like you to have is regularization, mainly, it has some other things that help us computationally, but other than that, its main point is to help us with overfitting. As I've said before, overfitting is a consequence of having a finite amount of data. The more data you have, the less overfitting is supposed to worry you, because overfitting is learning some peculiarities of the particular training set you have. Thus, as n gets large, my regularization should become less important to me, at least the computational benefits aside. And that pretty much happens because our term on the left, our data term, loss term, data fitting term, whatever you want to call it, is a sum over a bunch of training examples, n training examples, and the other term is just lambda w squared, or norm w squared. So as n gets big, the data term is summing over more and more things, but the other term is just staying the same size. It's just lambda times the norm of a vector of length d. It has nothing to do with n. So that kind of makes sense. As n goes to infinity, that first term should just naturally become more important than the regularization term, which is good and something we kind of want. So there's also a Bayesian interpretation of this, where the regularization corresponds to a prior distribution on the weights. We don't really get into that. Oh, we a little bit get into that in this course, and we will talk about that. But if you know about that stuff, it maybe helps to think about it in that way as well. So having said all that, it's useful to have intuition about what lambda means. But if we're just going to set lambda with a validation set or cross-validation anyway, then in a sense, who cares? Because, well, we don't really have to sit there thinking, oh, what should lambda be? We're just going to pick whatever works best. But still, it's worth understanding what it means to have a bigger or smaller lambda. Okie dokie. Right, very short chapter to this bonus lecture. We've talked about the intercept and about the next set of sections is about shifting and scaling things. So one thing you could do is shift the target values by their mean. And then you could ask, well, do I not need an intercept? Or you could even ask a different question. Why do we even fit an intercept in the first place? Isn't it just going to be the average value? And I just want to show that it isn't. So here's a data set. And it's very clear what the best fit line is. In fact, there's a line with 0 training error. Same one as before. Y equals x, right? And in fact, I've set it up so that the intercept of that best fit line is 0. It passes through the origin. Obviously, I've made up this data set. And so I can run it. I can call scikit-learn's linear regression, fit it on this data set, print out the intercept. I get 0. That's exactly what I expect. I could print out the coefficient, and it would just be 1. I don't even know why I'm doing this, but it should be 1. It's just the slope of the line. Okay. And yet, the mean of the y values is not 0, because I put more points for positive y than for negative y. So all I'm trying to say here is, yes, there is a point in having an intercept. It's not just going to always equal the average value. Okay, so that is shifting the target values. Now let's talk about scaling the input values. We're not going to talk about shifting the input values, but at least for linear regression, the intercept should sort of take care of that for us. Okay, so here's the situation, okay? I create some fake data set, that's this code. Then I call linear regression with normalize equals false, which is the default, meaning don't touch x. And then I call it again, normalize equals true, which scales, and I don't know if it also shifts, but it doesn't really matter, I think, the features. And then I check the following. On some randomly generated test vector, am I making the exact same prediction in the two cases? And all close, I'm not checking if they're equal, because numerically they might be off by machine precision or something. So all close just says, are they pretty much the same? And they do, because for regular linear regression, if I scale the features, if I take feature 1 and multiply it by 2, I can just take that w and divide it by 2. And the product of those two things will stay the same. So I'll just get basically the same model. Now I can do the same for ridge. And it's false. And we talked about this. I just wanted to show it. I know we already talked about it. I already said it in class, but I just want to show it that with ridge, if I scale the features, then, well, with ridge, scale actually matters, because I remember there's this penalty term, regularization term, which is summing the squares of all the w's. So I can't just say, oh, I'll divide the w by 2 and everything will be the same, because the regularization will say, oh, that's different, and maybe this isn't a solution anymore. Maybe I divided a feature by 100, and so I multiplied the w by 100, but then the regularization term says, oh, I'm not happy with such a big w, I'm going to push it down, and so I'll actually get a different solution. And yes, I know I'm personifying. I slipped from personifying, I don't know, models to not even regularization, but that's okay. So what's going to happen here? Right. Same thing with L1 regularization. The scaling does actually change things. And in general, it's a good idea to scale your features unless you have some particular reason not to. And there are reasons not to, like if you have sparse features, you have a giant data set that wouldn't fit in memory except for the fact that it's sparse, and therefore you can store it because it's mostly zeros. But then if you, okay, maybe not scaling, but if you try to do something like subtract the mean, which you should actually do before scaling, then all those zeros would become non-zero and become a mess. That's just an example. A mess because it would then be too big to store. Okay. I don't remember what this is about, even though I probably made it yesterday or 2 days ago. Let's see. Okay. Cool, fine. Here's an example that my past self created. It has 2 features and 2 points, and no intercept for simplicity. And the solution in this case is pretty clear because of the 1, 0 structure, the diagonal structure of x. We just set w1 to 1 and w2 to 1,000, and we 1 over 1,000, and we get 0 training error. If you multiply x times w, you get exactly y. So I construct this data set, and I get the expected coefficients, 1 and 0.001. So now we can run ridge, meaning linear regression with L2 regularization on this same data set, and we get this. So that's interesting. Oh, I see why I made this example. Okay, I made it as an example of you have 2 features of different scales, and which is related to the idea of scaling features. So if you have features of different scales, what does that mean? And right. So when I run ridge on this, you can see that the big coefficient got pushed down a lot, and the little coefficient got pretty much left alone. And that makes sense because it's, remember, a squared penalty, so it's not really upset about w equals 0.001. W squared is 1 over a million. That's not very painful in the loss function. So it's much more worried about pushing down the 1, which is exactly what happened here. It got pushed to 0.5. Right. So we can do the same thing with L1 regularization, and we get similar results. So I think it requires a bit of careful piecing it together, but what I'm trying to say here is that after I add regularization, the ratio of the coefficients is no longer 1 to 1,000. And therefore, if I had scaled my features to be, I see now, okay, it's all coming back to me. Had I originally left my features and say they're this, had I changed this 1,000 to a 1, the answer would have been w equals 1, 1. So in other words, the 2 coefficients would have been the same because everything was nice and symmetrical. And so what I'm saying is when it's 1,000, because the regularization pushes differently on the big and small coefficient, the ratio of those coefficients is no longer 1,000 to 1. And yet, had I first rescaled the data set, in other words, set normalize equals true type thing, so that the feature would become 1 instead of 1,000, then by symmetry, with regularization, I would have gotten the 2 coefficients to be the same, which isn't the same model as this, because then when I unscaled it at the end, it would be a 1 to 1,000 ratio, and here there's a different ratio. So this was a somewhat botched appeal to your intuition about why scaling matters with regularization. Okay. So let's talk about scaling the y values. This was something that Gurinder asked about in class and caught me a little off guard. And it's an interesting story. Okay, so I'm doing the same kind of thing, but I'm just going to scale the y value. So look at this. Here's the code. I fit the linear regression. And then I fit another linear regression where my y values are just multiplied by some scale factor, like 10. And then I check, again, the same test I was doing before, except I take my predictions for the second one. So I took the y values and multiplied them by 10 during training. So when I make predictions, I better divide back by 10 to get the same predictions as I would have gotten, right? So that's why I have this divided by scale factor in the prediction. And now I'm going to see if they give the same result. What do you think is going to happen? Right. Not a big shocker, I guess. So everything's linear. I don't know. Okay, and it makes sense. I don't expect you to be too shocked by this outcome. And I can do the same thing for ridge regression. So it's the exact same code except with ridge. And it's still fine. And then I do the same thing with lasso. And suddenly, it's not fine. So that's good to know, I guess, maybe. Scaling the y values actually did something for L1 and not for L2. Whereas scaling the features did something for L1 and L2, changed things. So what is going on here? Yeah, or as my daughter would say, what's going here? It's kind of cute. Okay, but it's weird. Anyways, it's weird with empty room. So that's a lot of equations. How about I try to say it? For regular linear regression, if I take y, multiply it by some value, I could just multiply all the w's by the same value. If y is multiplied by 10, I can multiply all the w's by 10. Then my predictions, which are just a linear function of my w's, will also be multiplied by 10. And just everything about the problem will be multiplied by 10, and everything will be kind of the same. The w I pick will be the same. My predictions will be the same as long as I correct for the scaling factor at the end. So that's what this says. For no regularization is fine. Then for ridge, I'm being a little more precise about it. I'm saying, what if I replace w with c times w, right? Because that's what I'm claiming will get the job done. If I multiply y by c, let me also multiply the weights by c. So my loss of c times w is, yeah, this should be, this is a bit sloppy. This should say if I multiply y and w by c. It's not quite written there. But okay, I multiply y and w by c, then the stuff on the left, because it's all squared, I pull out a c squared. And with this regularization, since I multiply w by c, then I also get a c squared. And so in the end, I just get the exact same loss function, but multiplied by c squared. And I can scale my loss by a constant, and nothing doesn't change anything. So that's the idea there. Everything's just the same. With lasso, I can do this, but because the left term is squared and the right term is not squared, if I multiply y and w by some constant c, the loss is actually different. The power balance between the regularization term and the data term has shifted because my scaling affected the data term by a squared amount and the regularization term by a linear amount. So, great. What's interesting about this is if we just gave another factor of c to lambda, we could actually correct this problem. So in scikit-learn, what we call lambda, they call alpha, and by default it's 1. So if I set alpha to be multiplied by that same scale factor, and then I rerun the experiment, then they actually work out the same. So in other words, when doing lasso, if I scale my y values, that implies a similar scaling on lambda. And in conclusion, we might not care about any of this because if we're picking lambda by cross-validation anyways, then as long as we've scaled our y values before picking lambda by cross-validation, this seems a little bit irrelevant. but interesting to contemplate. Okay, collinearity and conditioning. So we kept saying in class, let's imagine these two columns are a copy of each other, and people kept objecting, well, when is that actually going to happen? And so I just wanted to address that question. So first, if you haven't heard of the condition number, say from Computer Science 302 or something like that, it's just a measure for a matrix of how you want the number to be small. And as it approaches infinity, the matrix approaches being not invertible. And when it's very big, then when you're solving a linear system with that matrix, little changes in the matrix can result in big changes in the output, which in general we don't want. And we'll talk about that in a minute. So here I take some random data. I set the first two columns to be the same. Excuse me. I get a huge condition number and a crash when I try to take an inverse. The thing is not invertible. We talked about that, and that is fine. And I can also make column feature 0 a sum of all the other features, and I still get some very large condition number. Shouldn't it be invertible? Is that definitely true? Probably. Okay, so this dummy variable trap, if you haven't heard of it. So one case where this arises in practice is we talked in the second lecture of the course about we showed this Titanic data set, and we said to convert the categorical variables to numerical variables, we can make these dummy variables which look like this. So instead of town that you embarked in being some categories, you have, did I embark in this town, this town, this town, and you just have a 1 for the town and 0 otherwise. Well, okay. We'll get to in a minute why that's a problem, but first, why is a condition, okay, I got things a little out of order, but okay, why is a big condition number even worrying? So here's a data set where I'm trying to predict that first column of that Titanic data set given the rest, and I call linear regression, I store the coefficients, then I make a tiny perturbation to the last column of x. I just change it by, to the first training example, last column, just 10 to the minus 8. That's not good because I didn't rerun this. Okay, good. Need to rerun that. Yeah, so it didn't work because I didn't actually run the code that created the dummy variables. Okay, now I ran the code that created the dummy variables. And when you have this mess with the Titanic data set, look at what happened here. I just changed one entry in my features by an insanely small amount, and my coefficients changed by some decent amount, like 0.5, before and after. So that's what high condition number does and why we don't like it. Because how are we supposed to trust W? I can't go tell someone, hey, I did your work for you, and W is 0.7. And they're like, oh, really? But if I change this feature by 1 over a million, then now W is 0.2? How can I trust that you said 0.7? Right? If you take a statistics course, you'll talk about confidence intervals and all these kinds of things. That's very related to this, but now I'm talking about it more from a linear algebra condition number point of view. But they really, they meet in this application area. Okay, right. So the intercept, as we talked about, is we add a column of 1s. And now we have this, remember, collinearity, it's about one linear dependence. So now the third column is the sum of the first and second columns. And that's exactly this, rank, the matrix is rank 2 instead of 3 type thing that causes the problems. And indeed, once we've added the intercept, we have this huge condition number and everything's all messed up. So this is a common case where it can arise in practice if you use something like this dummy variable thing and you don't drop first. So again, here with pandas, they just provide this drop first, which however many categories are, it just throws away one of the columns, which you don't need anyways, because that information is redundant with all the other information. And then things are not badly conditioned. So that's one way that it could arise in practice. there are others. Okay, so we can do, we had this horrible condition number when we didn't handle it properly. Regularization also helps with this. So we talked about regularization helping with this, and we can see it helps with this. Getting a bit low on time, and I don't know exactly when the camera shuts itself off, so I'll try to get through everything. Okay, so we can look at what regularization does to this. So I made a data set where the first 3 columns are the same as each other, and then I can fit linear regression. I look at the first 3 coefficients, and they're this horrible thing that we talked about where they're just these giant values, positive and negative, canceling each other out. So scikit-learn's linear regression is exactly doing this thing that we feared, and it's not really scikit-learn's fault, it's our fault for not using regularization, which we should pretty much always use. So if we do ridge, not only are the coefficients not crazy, but it's exactly what I had claimed in lecture would happen, that the coefficients would be equal, so they're each around 1/3. In this case, the true coefficients, should be, well, there should be a weight of 1 in total. And all the coefficients are equal, and they're equal because having 1, 0, 0, or 0, 1, 0, or a million, negative a million, 1, or whatever, all those have a bigger penalty. Remember, it's the sum of the squares of the coefficients. That's what L2 regularization is. So having them all equal gives us the smallest sum of squares of W, so that's why L2 regularization picks this specific way of resolving the ambiguity of having the coefficients all be the same, and therefore they're all, you know, in this case, 1/3 of whatever the total actually needs to be. So with lasso, we don't have this equal sharing. It's not, the argument I just described doesn't apply because, for example, here 0.0700, or now I'm going to switch it to 0.07, or having them all 1/3 of that, 1/3 of that, 1/3 of that, those all have the same L1 because I'm just adding up the absolute values, right? Like a third plus a third plus a third is the same as 1 plus 0 plus 0 is the same as 0 plus 1 plus 0. That's true when you're taking absolute values, but not true when you're squaring. So here, that's why we said in class with L2 regularization, the solution is unique, and with L1 regularization, the solution is not unique. And indeed, I can compute the accuracy, and I can reverse those 3 coefficients, so put the non-zero one somewhere else, and compute the accuracy again, and it's the same. So to show, I'm just saying the loss didn't change when I changed the coefficients, which is another way of saying the solution's not unique, because these are all solutions. They minimize the loss. Okay. Right. So another question is about overfitting in linear models. So what does it even mean for a linear model to overfit? Because it's just linear. I mean, how complicated could it be? Overfitting is like, ooh, crazy squiggles, RBFs, right? High degree polynomials, but this is just a line. So what does it even mean for a linear model to overfit? There's a lot of text here, but the punchline of it is that when we have a lot of features, since in linear models we have 1 parameter per feature, then we have a lot of parameters. And in fact, if we have, for example, n features, then we have n parameters, and then we can always get 0 training error, because we have n. 0 training error means what it says here, x w equals y. It means our predictions equal our y values. We have n y values, so we have n equations that need to be satisfied, and we have n free parameters because we set d equals n, or plus minus with the intercept, but roughly we set d equals n, so there's n w's, so there's n free parameters and n equations, and it's linear, so we should just be able to solve it. There should be a solution, meaning that with that many features, d equals n, we can just get 0 training error no matter what. Well, not exactly no matter what, but roughly. not worrying about collinearity for a minute. And so that sounds like overfitting in the sense that always getting zero training error kind of sounds like overfitting. So they're still linear models, still hyperplanes, but they can get arbitrarily complicated by inflating the dimension to be however big you want, and then even a hyperplane in such a high dimension is still complicated. Okay, yeah. So here's what I'm doing. I'm making a data set where I'm just, the true thing is just y equals the first feature plus some noise, and then I'm just adding random features, more and more random features to see what's my training error with more random features. And as you can see, when I just keep adding random features and fitting a linear model, I can get zero training error. So that looks to me like overfitting in the sense that I'm learning all these coefficients for all these random features and doing better and better. So not having those random features, I couldn't get zero training error. And now that I have them, I can. But is that added complexity real, or is it overfitting? Well, here it's overfitting because they're just random, they're garbage. And so that's sort of what a linear model overfitting looks like. Okay, very last thing is just this plot picture I made in response to a question on Piazza, and I just wanted to highlight it in this video, which is people often ask about when can I use the normal equations, when can I use gradient descent. So I just wanted to show this picture. When I say optimize with gradient descent, I mean in this course, not trying to apply that we should always use gradient descent. I've talked about this before in the videos, and that's definitely not true. But for this course, there's convex functions, there's smooth functions, there's the intersection of them. And then within that, there are quadratic functions. Quadratic functions such that the gradient is linear, such that we can solve it by solving a linear system. Pretty much linear regression with or without L2 regularization is the only thing in that category. Outside of that category, we have, say, the Huber regression, which is kind of like the next easiest thing because it's still smooth and convex, and we can just use gradient descent. And especially if we're picking our step size reasonably, we should do a good job of solving it. Then there are functions that are convex and not smooth, like when we use the absolute value loss or lasso. And I should have had another category for stuff with unique solutions. Like that would have been interesting. Anyways, because remember, just because it's convex doesn't mean there's only one solution. And then there's smooth but not convex. And I think we haven't